of the Moon, now on BBC One, in the sky at night.
Good evening. Back to the Moon. Last month, we talked about the chances of finding tiny droplets of water inside the top 2 millimetres of moon crust. Well, there are some people, not me, who believe that down deep inside the surface there are large quantities of water ice. And a special experiment was worked out to find out whether or not this was true. While it was going on, I was on the beach in Selsey. Chris was in California.
LCROSS launched on the same rocket as the Lunar Reconnaissance Orbiter back in June earlier this year. While LRO's mission is to map the Moon, LCROSS piggybacked on the otherwise redundant Centaur rocket stage. The plan was to separate LCROSS from the Centaur and use the rocket stage to impact the lunar surface deep inside a crater near the south pole of the Moon. The much smaller shepherding LCROSS craft was designed to follow close behind, attempting to observe the plume of dust from the first impact in various wavelengths. There would be just a few short minutes for the probe to send the data back to Earth before it too would crash onto the lunar surface. The data could provide much sought-after evidence of water ice. In just a few hours' time, the LCROSS spacecraft will smash into its target crater near the south pole of the Moon. To watch, we've come here, to Palomar Observatory in California. Behind me, in this imposing dome, is one of the world's most famous telescopes, the Palomar 200-inch.
Tonight we're planning a high-resolution movie of the LCROSS impact. So the idea is that most observatories are actually going to be searching for the water in the impact debris using spectrographs. And as we have adaptive optics here, which gives us very high spatial resolution, we're hoping to basically show where the debris is for all the other observatories. So our plan is to use the adaptive optics system with an infrared camera, taking images every 1.5 seconds or so throughout the whole impact.
And you mentioned adaptive optics. What are adaptive optics exactly?
The idea is that the Earth's atmosphere distorts the light passing through it, much like water does, distorting light going through a swimming pool. And we use a deformable mirror that's controlled very rapidly and apply opposite shapes on this deformable mirror to the distortions to cancel them out.
And you have to do that very quickly because, of course, the Earth's atmosphere is changing.
That's right. We have to do it quicker than the wind blows across the telescope, essentially, so about 1,000 times a second. Our entire program tonight is a bit experimental, and so we're hoping it'll work out. We have to lock on a bright sunlit peak on the Moon, which is something that we've only done once successfully before. We hope it'll work a second time.
Choosing the crater which would give LCROSS the best chance of finding water ice caused more than a few arguments. Eventually, the team decided to crash the Centaur into Cabeus, but that's a difficult crater to see from here on Earth. So why Cabeus? Out of all the craters on the Moon, why pick on this poor, defenseless little one down at the South Pole?
It's obviously extremely important when you've got one shot to do this to pick out a crater that's going to be most useful. The first thing, obviously, was to get a permanently shadowed crater. That was the key to the whole experiment, looking for ice. But then you also want to maximize the geometry so that you can see it from the Chase spacecraft, so that you can see it from some of the really big telescopes on Earth, like where we are at Palomar. And then they got into even more details of the geometry so that the lighting, when the plume comes up, not only do you get that sunlit, but you have some of it against a dark background.
So how would the water have got there? It's not from the Moon itself, presumably.
Right. We presume if there is water ice, it's probably mostly been delivered by comets and impacting over the course of the solar system history and depositing their water ice, among other things. And then that water migrating, every time it gets heated up by the sun in the lunar day, it basically vaporizes, and then water molecules go flipping along, and then they condense again in the lunar night, and eventually the theory goes, they find these nice stable places at the poles and these permanently shadowed craters and may just hang out there for eons.
Tonight's impact is a unique event, so it's not surprising it's attracted the attention of amateur as well as professional astronomers. We're very lucky in that we've been joined by a crack squad of Californian observers and imagers, all here to enjoy Palomar's famous skies. Nice telescope.
Thank you.
It's looking ready for the evening. What are you up to?
Well, right now I'm trying to set up everything I'll need for tonight's event. Hopefully I'll be able to capture it take place. This is a 12-inch telescope, which is the minimum size we'll need for being able to look at the crater area that the impact is going to take place.
To see Cabeus, that's correct. That's the crater.
Yes, and if we're lucky, we'll catch it on film, and some of us will catch it visually, hopefully.
Hiya, can we interrupt for a second?
Sure.
How are things? What are your plans for the evening?
Well, unlike most of the folks here, my main emphasis will be getting visual.
Fantastic.
Okay?
Proper
Now,
astronomy.
Well, there's all sorts of astronomy going on.
Sure.
I'm coming up here, and I'm going to be pointed this right at the moon, and I'm going to be just seeing if I can catch this on my homemade telescope.
Fantastic. Classic Dobsonian.
Yeah, it's a classic Dobsonian, and it's a 12.5 incher. This I'm going to remember, I saw it with these Mark I eyeballs.
As the sun sets here on Mount Palomar, you can feel the excitement building. It will still be daylight in the UK at the time of impact, but it should still be possible to see the resulting plume if the NASA predictions are correct. And that's exactly what Patrick's planning to do in Selsey.
We're all down here on the end of Selseyville, and it doesn't look good. Last night was lovely, but I'm afraid at the moment we're clouded out, but you haven't despair yet. Well, what do you think about this, Paul?
Oh dear, it looks pretty hopeless, doesn't it, I think? But it might clear.
You got a drawing last night, Paul,
I
didn't you?
did, if only we had those conditions now. Seeing's not great. You can see how foreshortened it is on the limb. You'll know that's your time as a moon mapper.
I do indeed.
How foreshortened it is. It's not an easy target.
I think, Pete, you were pretty hopeful, weren't you? Have you had clear weather?
I was very hopeful, Patrick. I've actually got an image which I took
Yes.
the morning before, actually.
Oh,
so
yes.
that was yesterday morning when it was very, very clear.
A big crater of Mauritius.
There, and then this dark patch here is actually where the impact is going to take place. And it's quite easy to find because there is a very distinctive mountain on the limb which picks it out very nicely. But it's a very difficult region of the moon to identify because everything is so foreshortened.
Well, I know the region. I've been mapping it for many, many years, but it's really a difficult one. But you certainly know that it is there, and it's the right kind of crater. All we need is a gap in the clouds. Of course, over in America, because they are almost clear scales and have bigger telescopes than we have.
Indeed.
So they should see it, and they should get the analysis, but I still maintain we are not going to find any water. If they do, I really will eat my hat.
Well, the good news is it's a beautifully clear night up here on Palomar Mountain, so hopefully things are looking good for our chances of observing the impact. We've switched to a special infrared camera so we don't disturb the observers, but let's go and see how they're getting on. So how does it look?
Very clear, very stable. Yeah, it's wind has died down, and looking at the region where the Cabeus crater is, so I should be able to see the impact.
So here it is. Is this the target region?
Yeah, this is. I'm using two reference points, Clavius and Mortis, and this ridge area here. So generally, this is probably where Cabeus is at, and hopefully, if we're lucky enough, and again, this is not the 200-inch telescope, we might get some of the plume coming off the surface, which would be very exciting for us.
What do you expect to see when the impact happens?
Hopefully something, like everyone else.
Here in the control room at Palomar, it looks like the hours of preparation have paid off. The team have a beautifully clear and stable view of the impact site thanks to the 200-inch telescope, and meanwhile, the amateurs outside are readying themselves for this unique event.
30 seconds.
The LCROSS craft separated from the Centaur rocket stage a few hours ago, and both are now on collision course with Cabeus, down near the south pole of the moon. So the rocket should be somewhere in the field of view around now, so just seconds to go. It's there somewhere, heading for the crater. Finally, the moment we've been waiting for.
All stations flight. Mark, Centaur impact.
Well, I'm afraid the crash is happening at this very moment.
Yeah, we're not sure from NASA whether the impact's actually happened yet or not. It's supposed to have done.
Well, one way or the other, it's exciting.
Yeah, absolutely.
We get a confirmation of an impact, somebody give me something. I got nothing.
This will be the ultimate negative result if you can smash something into the moon and not produce anything. That's bizarre.
Well, I think I can see it. Kind of it's small, but it's getting bigger.
But there's absolutely no sign of anything, is there?
The plume is mysterious.
So this image that we're watching from NASA TV on the screen on the small screen there, this is from LCROSS itself, right? So,
right.
So this is the following
shepherding spacecraft, as they call it, and it is clearly headed in and headed to its doom.
Well, it's now several minutes since the scheduled impact time, and we haven't seen anything yet from the giant Palomar telescope. But outside, the amateurs think they've spotted something.
I see it. I did get something, I believe. It's small, though.
Yep, that's it.
This is it, isn't it?
Yeah, that's it. That's
Yep.
how it's coming out on mine.
Yeah.
Yep, we got something.
So looking at the first comments from people looking at the camera images, there's no obvious plume in the LCROSS images. There may be stuff there, we'll have time to process these, but I think it's fair to say that the whole result of the impact is a much, much less spectacular plume than we expected.
We just received flight shepherding spacecraft impact. Stations report LOS.
Everything seemed to work perfectly. It's a technological success, but we've got a scientific result that we just didn't expect. The reality of the situation has begun to dawn on the amateur astronomers outside.
I'm not seeing what those guys are seeing.
I don't see anything really easy to say, yep, that video captures a dust plume.
Did we see something? Is it maybe we wanted to see something? If I'm disappointed, absolutely. And embarrassed.
Here we are.
Hello. We were totally unlucky. What luck did you have?
Well, did you have clear skies, Patrick?
We were totally clouded out, not a break in the sky. We were all ready on the end of Selsey, everything set up, and not a chance.
I have to say, Patrick, the news is that I don't think you missed very much. We had clear skies here, beautiful image of the right region from the adaptive optics, but saw absolutely nothing. And indeed, we've been watching NASA, and the spacecraft didn't see very much either. There's no sign of a plume, only a signature in the infrared. So I'm not sure what any of that means. What do you reckon?
I don't understand it at all. Thanks very much, Chris. All the best.
Right, take care, Patrick. Sorry you were clouded out.
And sorry you haven't had more luck.
This beautiful sunrise with Venus, Saturn and Mercury hanging there marks the end of an intriguing night. Everything worked with the spacecraft, everything worked here, but we didn't see the plume we were expecting. And what that means, well, we don't know right now. To try and understand why we didn't see a plume of dust and ice particles as predicted, I'm making the trip north to meet up with some of those responsible for the mission. I first met with cratering expert Pete Schultz here at Ames Research Centre in 2007, where he was creating impact craters in the laboratory. And the first thing you see is nothing.
Right, it's just dead black. But then we have the flash. That's the moment of impact. And now we see that heated material, then suddenly we begin to see material coming into the sunlight.
So this has been thrown up enough that it's into daylight and we see the scatter.
Now the ejecta is rising above that rim of the crater. And you notice that we still see some hot stuff on the floor.
Peter's lab results seem to promise us a huge plume of dust visible from Earth, but we didn't see anything at all. We saw some of this flash, at least in the infrared.
Yeah.
What did we see compared to your laboratory measurement?
Yeah, but this is what we're still studying. We're still trying to decipher exactly. A lot of these instruments need to be properly calibrated, but I can tell you we're happy
Well, we were certainly surprised at Palomar that we didn't see anything. Were you surprised by the lack of visible plume from the Earth?
Not really, not for this site, not for this particular site. I think if we had been in a different place, we may have had a shot to see something. The amateurs could have seen it. This was a tough place for observatories to see.
What is it about the crater that made that so difficult?
It was really deep. It was a deep shadow, and there was a mountain in front of it. Those two things in combination made it very difficult to see from Earth. The debris has to get into sunlight and needs to be visible from the Earth. This clearly got into probably some light, but the reason that's important, the water molecules will boil off, in a sense, off these sand grains, and then that would then allow us to see it.
So one explanation is that all the activity that you've been describing happened before anything came clear of the mountain.
Exactly.
I've come to the home of LCROSS, NASA's Ames Research Center in Silicon Valley. We're told the Centaur rocket stage impact provided plenty of data for LCROSS, and I'm hoping that Principal Investigator Tony Colaprete will be able to tell me what they've learnt so far. So the Centaur hits the moon, and then a few minutes later the shepherding spacecraft LCROSS follows. What instruments did it have on board to study the impact?
We have 9 instruments. Those nine instruments include 5 cameras, a visible context camera, just told us where on the moon things were so we can put everything in context. 2 near-infrared cameras, they're at 2 different wavelengths, inside and outside water vapor bands. We had 2 thermal cameras, also inside and outside water bands that measure temperatures. And then we had a total luminescence photometer. That was a very fast photometer that measured total integrated visible light. And it was a flash detector. It was meant to detect the flash. It made 1,000 measurements per second.
So it did detect the flash of the Centaur rocket?
It's not clear yet.
Okay.
And that's an interesting point. Without a flash, one way you can get no flash is there's a lot of volatiles. A lot of energy has gone into subliming, evaporating materials instead of into visible light.
So let's see if I understand this. If you hit something that's just pure rock, then the energy goes into creating the flash. But if you have ice there, that energy gets used in vaporizing the ice.
That's right, and the heat's going into either making light or evaporating water. And if it's evaporating water, you'll get much less light.
But you did see the impact with the thermal cameras.
Yes, we did, and with the spectrometers. We have 2 spectrometers look straight down. One's in the ultraviolet and visible light wavelengths, and one is in the near-infrared wavelengths. Both of them saw the impact flash and the ejecta plume that followed. We saw in our thermal cameras the impact flash, so we were able to measure actually the temperature of the plume at impact. And what we're measuring there thermally is actually the vapor plume of the impact and the fine debris coming up from the impact flash itself. It's a very rich data set. In the first 3 seconds of that impact, we actually probably have enough data there to answer all the questions we were after. A good experiment is one that you don't expect. The results are unexpected. We certainly got unexpected results, but we got enough data to unravel the unexpectedness of the result.
Well, Chris, you're back from California. What's the latest news?
Well, it's been fairly quiet since I talked to Tony a couple of weeks ago. I think they've been working hard to look at the wealth of data that he described. Firstly, I think it's become clear quite how well the LCROSS spacecraft worked.
Everything worked beautifully.
Yes, and right down till the moment of impact.
And of course, it came down in exactly the right place.
It did, but it didn't produce the effects I at least was expecting. No plume. Did that worry you at the time?
It didn't. I thought probably it had gone through a bit of the surface, had landed and gone off bang, but by that time it was covered by debris falling from above.
There's one possibility. Some debris definitely got up. We know that now. Some of it was observed by the Lunar Reconnaissance Orbiter flying overhead, which also saw the results of the impact. So everything we need is there. The question is, did LCROSS see water? And I'm guessing, but judging by the grin on Tony's face, I'd be very surprised if they don't announce sometime in the next few weeks that they've seen water.
Well, I wonder. Possibly by next month, we'll know. Well, Chris, thank you very much. So, until next month, good night.